So welcome to this InterCAD webinar. Today we're looking at Simulation Express versus Simulation Standard. My name is Ilcha Jovanov and I'll be taking you through this webinar today. I am a field engineer for InterCAD based in Melbourne. So having a look at Simulation Express versus Simulation Standard, just looking through this now. So simulation basically is part of the SOLIDWORKS suite of products, and what we have is Simulation Express, which is basically part of the every license that you can get in SOLIDWORKS. So if you've got SOLIDWORKS Standard, SOLIDWORKS Professional or SOLIDWORKS Premium, you will have Simulation Express. Where you can find it, I'll just switch to SOLIDWORKS here, and if you go to your Evaluate tab, you should be able to see all of the Express products towards the end. Simulation Express is that option there. So we also have Flow Express as well as DriveWorks Express there. Now how you can get access to Simulation Express is through a code, and the code can be obtained using an account that you need to create at mysolidworks.com. So if you haven't done that, if you click on Simulation Express, this will ask you for a code that you can create, and it will actually give you a link to go to mysolidworks.com and create an account. Now the prerequisite for that is you need to have you need to be on subscription, so your subscription needs to be active with us, and that will give you access to all of the Express products. So the account basically controls whether you have subscription or not, and therefore giving you access to those options. SOLIDWORKS Simulation Standard, that is available only in the premium version of SOLIDWORKS. Okay, and SOLIDWORKS Simulation Standard is basically FEA analysis static. FEA analysis. So, so that's the difference between the two and how you can access them together. Now, SOLIDWORKS Simulation Express, basically you can think of it as a version to the, as a demo version to the Simulation Standard, in that it will let you do an analysis, and you can view the results and you can see how the model reacts to that analysis. However, it does lack quite a lot of options and settings, and we're going to go through these today and basically what the difference between the two is. Okay, so having a look at my slide here and going through what simulation basically is and how it works. So we have a mathematical model, that is your SOLIDWORKS model that you design, okay? And simulation will take that model through a discretization process, which is basically dividing the model into small pieces. These are called elements, and it can then analyze these elements, analyze how they interact together, calculate the forces between them, and therefore come up with a result as to how certain forces or stresses are propagated through the design. So we have three major steps. We have the pre-processing, which is basically designing the model, as well as dividing it into small elements, which we call meshing. Okay, and then we have a solution, which is done using the numerical solver in SOLIDWORKS, and then we have post-processing. So viewing at the results, representing them in different ways, and analyzing them, making sense of these results. So the areas of focus today are going to be, well, licensing, we already covered that. We're going to look at some of the study options, okay? So setting up the study, some of the properties that are available in the different versions, and solvers there. Looking at loads, so what types of loads are available, fixtures, same thing, so what types of features can we use in the different products. Contacts, so this is model interaction, contact pressures and that sort of thing. Meshing, so discretization, focusing on certain areas of the model, okay, and also error. So the meshing is an important process in simulation because through that we can focus in on a particular area in the model. So the finer the mesh, the smaller the elements, therefore the more focused calculation in that area. And if we know that there is a problematic area or there are some stress concentrations in a particular area, then we want to look deep into that design, deep into that area, and find out what the results are. We can do that by controlling the mesh size. Also, the error is therefore controlled by the mesh size. Finally, we're going to look at a little bit of, well, some post-processing options. So how to view the results, visualizations of different results, plots and graphs, and that sort of thing. All right, so let's jump to SOLIDWORKS. And I'm going to be using this particular model. First, we're going to look at Simulation Express. I'm going to set up the study and do an analysis with Simulation Express, and then we're going to look at Simulation Standard. Once we've done both of those studies, we can go through and compare the results. Okay, so Simulation Express is that option there. Okay, so I'm going to start over, and so this is Simulation Express. It is basically a wizard-based approach, and we're going through a few steps. We have 6 steps here. We're going to apply some fixtures, apply some loads, apply the material, and then run the analysis. We're going to look at the results, and then we can also optimize the analysis in this as well. So it's fairly easy to use, and so we are in fixtures here. I'm simply going to go in and apply a fixture by clicking Add a Fixture. So this allows us to select the geometry. Note we only have one type of fixture that we can use, and that is fixed geometry. Okay, so I'm going to select my faces that I'm going to have fixed. So I'm going to fix the internal faces of this hand wheel. Click OK. So a little bit of explanation as to what we're going to be simulating. So we're simulating this hand wheel being connected to a shaft at the hub. Okay, and then we also have a hole here simulating basically a handle going in. So we'll be applying a force at this point at a particular direction, and we're going to be holding this hub fixed, and that will obviously incur some internal stresses that we can analyze and have a look at. So I've applied my fixed geometry at the hub there, okay, and that basically simulates the shaft being in and resisting the motion of our handle. So next I'm going to hit this button, and that takes me to step number 2, and that is applying the loads. Now note I have the ability to apply only 2 types of loads. I have a force that I can apply, and I have a pressure that I can apply. In reality, there are many different types of loads, but in Express we only have these 2 that we can apply. I'm going to choose the Add a Force option. So I'm going to apply that internal to this hole, so to the inside face there, and this allows me to then apply magnitude, so magnitude in newtons there. Because the face is circular, what I also need to do is define a direction for the load. So I'm going to choose this particular option, so not normal to the selection, but we need to select the direction. I'm simply going to use my right plane there to define the direction of the force. So we have those little arrows there depicting the direction. And we also have the ability to reverse that direction, as you can see there. Now, we can only apply the force normal to the plane. We'll see in the full version, in Simulation Standard, we'll have some more options there. The magnitude of the load is going to be 1,000 newtons. Once done, simply click OK. So we've applied the fixtures, we've applied the loads. Hitting Next, I can now choose a material. By clicking this option, this takes me to the SOLIDWORKS material database, and the material we're using today is going to be a copper alloy aluminium bronze there. We can see all of the mechanical properties of the material here, including its yield strength, mass density there. Go on to apply this and click OK. So the Young's modulus of the material and the yield strength is there. Hit Next, and from here on we can actually simply just run the analysis. Note, meshing will be done automatically, so model will separate this step, which is actually a very crucial step in eliminating errors and in getting the accuracy level that we desire. So I'm going to simply choose this option, Run Simulation. So the process goes through the meshing and then it runs the study. As you can see, it doesn't really take much time at all, and we have the results. So we simply are being asked, does the part deform as you expected? If I hit yes, which it does deform as I expected, simply because we have a lot of movement in the area where I applied the load. Down the bottom we have a fixture, so no movement here, or very minor movement. So it is as expected, so click yes to continue, and then we have our results that we can view. Results are displayed in this folder. I can view the stress distribution, I have displacement, and I have a factor of safety. So 3 different plots that are available, and that's basically all I'm able to view. So stress distribution, we can have a look at that here. We have the color distribution, and we have our legend here. So I have the yield strength being 2.75 times 10 to the 8 newtons per meter squared, and we haven't reached that as yet. So I can see that the major stress is applied, or well, basically is at the corners of the spoke where I actually applied the load. Also, we can see on this side there is some higher stress distribution, so into that area there, but the major being the red area, which is there. If I look at my displacement, I can see that I have most of my displacement occurring within the rim and around this area, which is where the load is applied, so this can be expected. The maximum displacement is 3.59 times 10 to the minus 1, so 0.35 millimeters, not even half a millimeter there. Okay, and then we have factor of safety. This graph will show you in red where the factor of safety exceeds 1 in this case, and you can change that 1 from there. But basically, factor of safety is higher than 1 everywhere because we have no red regions. In fact, having a look at this node over here, we can see based on the specified parameters, the lowest factor of safety found in your design is 2.05. So there's no failure, 2.05, so just over double the load that the yield strength of the material will take. And this is how easy Simulation Xpress is. So you basically apply your loads, apply your materials, and then fixtures and run the study. So it makes it fairly easy, and it looks like simulation is an easy process. However, what we need to take into account is, in reality, whether this really represents what is happening. And if the answer to that is yes, well then this is a satisfactory result. So let's have a look at what we achieve in the full version of simulation. So just noting that this is 2.05 here. I'm going to close that, and I'm going to go into my add-ins here, and I'm going to turn on simulation. So this version of simulation, as I said earlier, is available with SOLIDWORKS Premium. And so what I have is some pre-created studies here, okay? And so one with no shaft. What I'm going to do in this case is rerun exactly the same study in my full version of simulation and see whether there are any differences, okay? So one thing to note is that this is actually an assembly. As with our previous design, that was a part. One of the limitations of SOLIDWORKS Simulation Express is that you can only analyze parts. You can't analyze assemblies, and you also can't analyze multi-body parts either. So it has to be a single body, which is why we're limited to only having to analyze this particular part. We can't put in the handle, and we can't put in the shaft so that we can see what the effects of having those two will be. So we're simply applying a load and a fixture on the model itself. Okay, so what I'm going to do is rerun the same study with simulation standard, and what I have is preset exactly the same settings. So we have the internal faces where the shaft would connect. They are fixed using a fixed fixture there, and we also have external loads. So the force is 1,000 newtons, equivalent to the previous, and it is applied on that face there. Okay. Now, if I have a look at my options with fixtures, in this case, I have fixed geometry, but I also have quite a lot of other fixtures. I have a roller slider fixture, fixed hinge, and elastic support, as well as these advanced fixtures here. So if I go to my roller slider option, you can see a bit of a preview as to how we can fix using that. We also have fixed hinge, okay, which will give us that type of fixture. And if I close and just go back to the next one, elastic support, this allows me to add elastic supports to particular entities of this model. And we have here stiffness in the normal direction, stiffness in the shear direction as well. And going to our advanced fixtures, this gives us quite a lot more versatility. So symmetry is one that's very, very important, because in this case we have the ability to simulate only half the model and use symmetry fixture in order to basically simulate the same result over to the other side as well. Also cyclic symmetry for circular bodies there. This is quite a big difference, because you know, a model of this size may take you a long time to fully study, whereas taking maybe a portion of it can take you quite a bit less time. Okay, and simulation could be very time intensive, and as we can see later on. And so as we add complexity to our design, the time will increase. We also have the ability to use reference geometry, you know, cylindrical faces there, so being able to apply or the radial translation there, circumferential or axial translation. So with all of these fixtures, you really have the ability to restrain the model, mimicking reality, and therefore giving you a much better result, much more accurate result than just having to use the fixed geometry. With the loads, in the previous one we only had force and pressure. As you can see here, we have quite a lot of different loads, so we can use torque, gravity, centrifugal force. We have the ability to apply bearing load, distributed mass, distributed load, temperature effects, any flow effects, and so on. So prescribed displacements there. So really, you have the ability to capture the full intent of the design using these loads. Now, the extra step that we need to take here is to mesh the model. This is something that we had absolutely no control over in the previous Simulation Express version. Here we do have control. So I'm going to right-click on my mesh, and what I'm going to do is apply some mesh control. Now, I already know where my stress concentrations are. They're concentrating around this area, and they're concentrating around this area here as well. Okay, so what I can do is tell the software, these are my problem areas, and I want you to focus in your calculation in these areas by applying mesh control. I'm going to apply mesh control on that particular fillet there, and I'm going to apply mesh control on the fillet here, just all the faces. In fact, to get a more accurate result, these corners, fillets, are all problematic areas. So what I'm going to do is actually apply mesh control on all of them. So just by selecting the faces, you can select faces, edges, so on. And I'm going to apply mesh control. And here you can select the element size, basically, and the ratio, so growth rate of the element from the control point to the global mesh size. Okay, and you can simply use this slider to move back and forth as well. I'm going to just leave it to my default mesh control size, 3.6 millimeters that is. Click OK. And then I'm going to apply a mesh. So right-clicking and I create mesh as well. Now, also we have quite a lot of control regarding the mesh. So we can use different types of mesh. Blended curvature-based, we have curvature-based or standard mesh. We also have the ability to add a draft quality or a full quality mesh there. Slider, again, using this to control the size, or you can simply type in the element size. We also have this setting here, so minimum number of elements in a circle, and once again, the growth ratio there. I'm going to reset this to just use the default mesh. Click OK, and then the software meshes my model. One thing to note here is that we have the global mesh, which is there, which is quite similar to Simulation Express, so it's quite large. But what we have is, as we can see here where the mesh control is, we have the elements becoming smaller and smaller and basically focusing most of the calculation in these areas. Same thing over here as well. So mesh control can have a profound impact on our results. Once we're done with that, I'm going to simply run the study and we can see the results there. Okay, so we saw some differences there, so different fixtures, different loads, okay, and I haven't even spoken about the connectors, which I'll talk about later, but also the major part being able to control the mesh size. And then we can see the results. Now, the results in this case can be viewed in many different ways. So we have 4 plots here by default, but I can right-click on any and actually apply any number of plots. If I say I want to define a stress plot, okay, then I have quite a lot of options. Well, what type of stress plot? What stresses do I want to show? By default, we can only see the von Mises stresses in Xpress, but here we can see quite a lot. So we can see the principal stresses, P1, P2, and P3. Compression, tension. We have the ability to see the different shear stresses in the different planes. The normal stresses on their own in the X, Y, or Z direction. Stress intensity we can see. Okay, contact pressure we can plot. So quite a lot of options there. If I go into some of the other ones, so we have displacement plot. We can see the different types of displacements, not only the resultant plot, but what if we want to see displacements only in the X, Y, or Z direction? What if we want to plot any reaction forces, resultant reaction forces there as well? So we have a lot of options regarding what type of data we show. Not only what type of data, but also how we show that data. So we can choose to show it as a vector plot there, have the ability to change quite a lot of settings on the chart. So what my minimum and maximum values are, showing minimum and maximum annotations there, a lot of different other settings as well, the ability to superimpose the model on a deformed shape so you can compare what the original shape was and what the deformed shape is there. So a lot of settings here. So let's go through and have a look at these results. My stress, I have 1.6 times 10 to the 2 megapascals in this case. If I have a look at my displacement, once again the displacement occurs around that area. And looking at my factor of safety here, okay, note the minimum factor of safety 1.72. Okay, and I have my graph here which can show the factor of safety a lot more clearly. In the first one, we only have the ability to show factor of safety that's less than a particular number. In this case, I can show it as a spectrum. So we can see where our minimum factor of safety is. It's in that area there, and a little bit in those areas here as well. But it has decreased quite significantly. So the original was 2.02, I believe, 2.06. This is 1.72. Okay, and that's basically around about a 16% decrease. And this is done by no other major changes except for the meshing. So I used mesh control in order to focus in my calculation on these areas and therefore achieve a much better result. Okay, much more accurate result. In this case, 16% difference. So for some, that might be an acceptable error, and it generally is if you're only trying to see where the weak points of the design are. So we can pinpoint even with Xpress where the local stresses are occurring at maximum and basically maybe add some material in those areas. Okay, but a more accurate result requires proper meshing and being able to visualize exactly where the problem areas are. So this is using no shaft, okay, and simply applying a global fixed geometry on those faces. Now, to put this in perspective, it's basically saying that no matter what amount of force you apply in this area, you're always going to have these faces being fixed, okay? And that assumption is not quite correct because you can't have an infinitely stiff structure, okay? We can also simulate that in an assembly, and I have a simulation here. So I'm using a rigid shaft, okay? So this is my shaft here, and now I am using multiple parts. So I have my hand wheel and I have my shaft. So simulation standard allowing you to use multiple parts to get a more realistic result. But what I can say here is the shaft, so I have the ability to right click, make it deformable or make it rigid. So by making the shaft 100% rigid, it's basically doing the same thing as we did in Xpress, saying that no matter what load is applied on the hand wheel, the shaft will always remain rigid, infinitely stiff structure. And of course, in reality, we don't really get that. And so what I have is the same load applied in the same position, but the fixture is no longer on those faces. The fixture is down at the bottom of the shaft. So we have a connection between these two. And the connection is governed by the connections options in simulation. This is an area that completely does not exist in Xpress, and that's because we can't have multiple bodies. So if I have a look at my connections, I have a global bonded connection. So these two being bonded, and therefore any load being transferred onto the shaft. Okay, but note the shaft is infinitely stiff. Just before we go on, looking at the connections advisor up on the top and seeing the types of connections that are available. So we have the ability to add contact sets between any faces we want, and the types of contacts. We have the ability to add spring connections, pin connections, bolt, welds, so different types of welds, links, bearings, rigid connections, and so on. In the contact sets, I have the ability to use a bonded contact, no penetration contact, which is actually representing reality. So basically, if two faces come into contact, they're not able to penetrate each other. So in reality, this is something that we'll be using. So you have shrink fit ability here, virtual walls, and you have the ability to also allow penetration. So I'm going to just close that. And I've already run this analysis, and we can have a look at the results here. So I have my stress distribution. Okay, well, we might have to just rerun. I don't think this should take too long. Okay, there we go. So please note, everything is absolutely the same as the previous study. The only thing is we're now using a shaft. Okay, we have a bonded connection between the two, and the fixture is down at the bottom there. The stress is still 1.6 times 10 to the 2 megapascals, and if I have a look at my factor of safety, okay, 1.715, exactly the same thing. So we're actually, by using a fixed connection up on the top, what we're saying is that we have a shaft that's infinitely stiff, and the connection here is infinitely stiff as well, which in reality is not the case. So what we're actually going to do is look at a more realistic model with a shaft, and the shaft will not be infinitely stiff. It will be meshed, and it is calculated. So we have there, so it's not rigid at the moment, and we also have the global contact, which is bonded between the two. Once again, same force, and the fixture is down at the bottom. Looking at the results, okay, stress concentration has jumped from 1.6 to 6.1 times 10 to the 2 megapascals. Okay, a huge jump there. The maximum has shifted from this area here down to the bottom. Okay, so a more realistic approach gives us quite a bit of insight into where the real maximum stresses are. So our assumptions that this area should be infinitely stiff was wrong, and therefore, if I have a look at my factor of safety, okay, see the factor of safety has gone down to 0.5. Any factor of safety less than 1 means failure, and therefore our design is actually failing. So you can see you can get quite a different result depending on whether you're able to represent the model in its realistic state. So the difference between Xpress and the full version of simulation can be quite important. In the first case, we're not able to see the effect that the shaft connection will have. So in here we can see that as the wheel is being turned, the stresses increase around that area, and failure will occur within that area there. Now if I just hide my shaft, just hide that and just reset the view so that we can see the distribution inside that hand wheel only. So at the moment I'm looking at the factor of safety of only the hand wheel and the stress of the hand wheel as well. Looking at this, I can do a lot of things with these results. So I can do a sectional clipping, I can do an isometric clipping, and I'll do an isometric clipping here. Basically, this gives me the ability to separate the model and find out basically where my my distributions are. Just turn that on. Okay, so let me just edit this again. Okay, there's a sectional clipping, isometric clipping there. And this is not working for some reason. Maybe I just need to rerun the analysis here. Okay, there we go. So we needed to rerun the analysis. And here we can see, just by moving my slider, I can see where most of the factor of safety or most of the failure is occurring. So up until about 1.6, 1.7, we have the factor of safety being reached down at the bottom. So anything after 1.7, which is what our initial result showed, is in that area up on the top. And just moving the slider here, we can see how the factor of safety propagates through. So this isometric clipping is a very good way to be able to understand where our failures are occurring. So this is what we've missed with the initial analysis, that area of the model there, and how it connects to the shaft. So I can turn and leave that on there. We also have the ability here, if I'm looking at my strain, so this the internal strain of the model, I also have the ability to define strain energy norm. If I turn this on, okay, what this does is this compares the nodal stresses with the elemental stresses, and it has the ability to show you where there's any error or where the mesh needs to be refined, okay? So having a look at this here, we can see that this area may require even more mesh refinement. So the mesh here should probably be smaller. The mesh control should be applied even further so that we can get an even better result. And more than likely, that factor of safety might drop slightly again. And so there you go, the major differences between Simulation Express and Simulation Standard. We can see that while we're able to do an overall ballpark analysis of the model in Express, this may not be the 100% accurate result. And looking at the results, I'm just going to go back to my page here. So we had Express versus the mesh control option in simulation, where the factor of safety was 2.06 versus 1.72. So 16.5% decrease in factor of safety just by the mesh control. And then if we apply the shaft and then do a more realistic representation of our problem, then we can see the factor of safety goes down below 1, and we have design failure. So these are some of the things that we need to consider when we make a decision. Do we use Express or do we move on to the full version of simulation? So just reiterating to conclude here, we have some of the focus areas. So with the study options, okay, basically we have absolutely no options in SimExpress, whereas Simulation Standard offers quite a lot of options. Loads, we have only force and pressure, whereas Simulation Standard we have force, torque, pressure, gravity, uniformly distributed loads, and quite a few more as well. With fixtures, we only have fixed geometry available, whereas here we have fixed roller, slider, hinge, elastic, advanced fixed geometries, so on. Contacts, we have none in Simulation Express because we can't use it in assemblies, whereas in Simulation Standard we have spring, pin, bolt, weld, links, bearings, and so on and so forth. Okay, so meshing, we have absolutely no control in Simulation Express, whereas in Simulation Standard we have full control of the mesh size. We have full control of the type of mesh. We have control of the growth rate. We also have control of the ability to localize mesh concentrations and therefore look deeper into the design. For post-processing, we have the ability to view stress, displacement, and factor of safety in Simulation Express, whereas Standard allows us to view the results in many different ways. We have a range of different plots that could really give us an indication of a lot of the effects within the model. Sectional clipping, isometric clipping there. We have the ability to probe the result on a particular location or a particular node. We have some chart options there and so on. So I hope that gives us a bit of an insight as to the differences between the two. Please, as you're using Express, be mindful that while you can get weak point locations on your design, the stresses may not be absolutely accurate. And if you do want to take that step further, well then Simulation Standard is your way to go. Going from Simulation Standard, we have Simulation Professional and Premium as well that deals with more advanced analysis, temperature analysis, for example, or fatigue analysis. Then moving on to Premium with dynamic analysis and nonlinear analysis, so composites and that sort of thing as well. I hope that was helpful, guys. Thank you for attending. And if you have any questions, feel free to contact myself or any of the technical support guys at Intercad. You can find the technical support number on our website. And yep, once again, thank you. If you have any questions, you can also type them into the questions area right now. So one of the questions, yes, I am recording this, so it will be available shortly on My Intercad, and you're able to go to My Intercad and either view it or even download this recording. For those of you that don't have My Intercad, please go to our website. It's a really good tool, very good for accessing all of our webinars and contacting technical support as well. All right, so if you have any more questions, please write them down. Otherwise, contact us. Thank you. Okay, so what is the link for the downloads? The downloads are given through an add-in to SOLIDWORKS called My Intercad. You can download this add-in on our website. If you just go down to the bottom, it'll give you My Intercad there, and just download this tool. What it is, if I show it in SOLIDWORKS, okay, if I go to Tools and just add-ins, it is this add-in My Intercad. Once I turn that on, it gives you an extra tab on the side here. And basically, this is our add-in. It's an Intercad add-in to SOLIDWORKS that allows you to contact us. Go to technical support there and type in a question, send it directly to us without having to go through emails or phone calls or anything like that. Okay, if I go back home and have a look here, so here we have a lot of videos that are available. Webinars is one of them, and one of these webinars will be posted. So this webinar will be posted here under the webinars option. This one that automatically starts playing is the last webinar. If I have a look inside, you can find hundreds and hundreds of webinars that we've done over the years going into SOLIDWORKS. See that we have subfolders, categories, and so on. So this is how you can get access to all of our videos by downloading My Intercad, installing it into SOLIDWORKS, and basically logging in. You log in with your email address, and that email address should be one that we have in our database. That's how software will recognize you as a customer and allow you access. If you want more information, contact us, contact the tech support guys. They will help you install this. It is a really good tool, so you can contact us very quickly. Okay, well, thank you for that. All right, so that's the link of the download. No more questions. All right, guys, have a weekend. See you.